Yeah, sorry, it's a bit late because I was eating. Yeah, can start. Sir?
Yeah, I know. I heard you. Been waiting for you already.
Sorry.
Okay. Yeah, now in 9.3 kinetic theory of pressure, we just need to know all this formula. We just derive this formula. So now we want the kinetic theory, kinetic energy of a molecule, which we will derive this equation, kinetic theory, half m, and then you can replace we'll derive this equation, c square equals to 3k over t over m, and m we can cancel to get our final equation. There's a value for c square. Okay, so that is we will derive this equation. Okay, so under this, it's always good to refer to syllabus. The syllabus tell you what is required. Sometimes teacher will teach, you may slightly go off our syllabus, right? Because you may interpret wrongly. Right? So we have already defined for you this equation. State and use the relationship between Boltzmann constant and molar gas constant. We've done that. Now we are going to derive this equation. Right? What does this equation represent? It tells us the average translational kinetic energy of a particle or molecule. Okay? Page 219, number 2. Right? Is the average translational kinetic of a molecule or particle. Remember, we are thinking of a particle, right? Or the molecule has only one atom. C is the speed of the particle, and this whole thing means mean square speed. K is Boltzmann's constant. T is absolute temperature. M is the mass of particle. Right? We can see from this equation, when T equals 0, the ideal gas has 0 kinetic energy. The substance is 0 kinetic energy or minimum kinetic energy, minimum internal energy for solid and liquid. Then use ideal gas, no kinetic energy at 0 Kelvin. But if it's solid or liquid, then we will come to define later on, right? It still has potential energy, so that's why it still have internal energy, sorry. Right? We'll cover this later on. Recall, right? We have derived this formula for you just earlier. Right? This one we obtained experimentally. This one we obtained from Newton's law of motion. Consider the particle as mass, speed, and number of particles. We have these two equations. We can compare these two equations. Right? It's good to know how because when we derive using kinetic theory, there's no relationship of temperature here. So it's good to know simple out there ideal gas equation, combine them to know how the kinetic energy or the speed depends on temperature. Okay, so these two equations are equal. N and N can cancel off. V and V can cancel off. So we get our, right, take the 3 across there, mc squared 3kt. So average kinetic energy of a molecule, right, we multiply by half here, we get this equation. Okay, so understand the formula is the average translation kinetic energy of a molecule is proportional to the absolute temperature, T. Any comment?
Oh, that's how you derive. No wonder you just like equate it and then later you times with 1/2, then you get the average translational kinetic energy.
Yeah,
oh,
that's what I'm doing.
I always thought you were so tough, like just have to memorize it. I didn't know you can just derive it like that.
Okay, make sure you know how to derive.
Yeah, now it's like easier to derive.
So absolute temperature from this equation is a measure of the mean kinetic energy of the gas particle. That's all. Right? Because we cannot measure this one, but we can measure absolute temperature. So this one tells
Which is
us
the mean kinetic energy,
mean kinetic energy of the average mean kinetic
Oh,
energy. That's all of the particle.
okay. Okay. K is a constant, is it? No, K is Boltzmann. K is Boltzmann. Yeah.
Right? The equation shows that the mean kinetic energy is directly proportional to thermodynamic temperature, which is capital T. So if your KT, EK is equal to 3/2 KT, this is the average translation kinetic energy of a molecule, then we can see that it doesn't, this one, there's no mass here. Right? Forget about this one. There's no mass here. There's a kinetic energy. So it doesn't depend on the gas of the molecule. So if we can have a mixture of gas in a container, all at the same temperature, then they have the same average translation kinetic energy. Okay? It doesn't depend on the mass or the speed. So to find the total, we just multiply by n here, multiply by n here. For n particles, okay? This is for one particle. We multiply by n, okay? Then multiply this one by n. We got n kT. Then our k can replace it with r over na. So our n over na is just a small n. Okay? That's the alternative equation. For ideal gas, there is no intermolecular force between the particle, so there is no potential energy. Okay? Its total potential energy is 0. So this is basically kinetic energy only. Okay? Energy is the total kinetic energy. Okay with that?
Okay.
Okay? Alternative formula for 1 mole. Okay? Multiply Avogadro's number Na on this side and on, sorry, that's the formula that we receive. Multiply by Na here, multiply by Na. You want to get this formula? Okay. Then this one is your MR, molar mass of gas, this one. And then this one is just your R. Okay, so that's the alternative formula. Then you just replace your K with your R as well, your M with your MR as well.
K with K and A is with R, so and MR is M and A lah.
Okay.
Yeah. And K and A is the R. It's all just playing with the formula.
Just playing with formula only, nothing much.
I thought I have to memorize the formula.
Just memorize the basic one and then derive the others. So if you don't want to memorize the others, because there's too many formulas to memorize. We have derived this part already. All this one we have derived. Now we are going to derive the other part. Okay, we are now going to degree of freedom and law of equal partition. Page 223. As I say, all these formula, the only way to remember them is to try the past year question. Okay, so instead of writing kinetic energy, we just put K. This is for one particle. So now we are coming to define the number of degree of freedom of a gas molecule. Identify the number of degree of freedom of monoatomic, diatomic, polyatomic molecule at room temperature. Explain the variation in number of degree of freedom of diatomic molecule ranging from very low to very high temperature. State and apply the law of equal partition energy. Right? Mean square speed. Right? What does it mean? It's just the mean or average of the square of the speed of all the particles in the container. So we have N1 particle with speed C1, N2 particle with speed C2, N3 particles with speed C3, and then NN particles with speed Cn. Then you should know how to calculate total number of particles. You just add all the N1, N2, N3, N4, and NN. Okay, so there's a total number of particles. Then N1 times C1 square, N2 times C2 square, N3 times C3 square. We just add them up. And NN times Cn square. That's all. Know how to calculate this value. Root mean square. Okay. Root mean square from here. We take our M down. And then square root this value. We get this value. Okay. It's the square root of the mean square speed. It's directly proportional to the square root of T. Okay. Know how to use the equation. This tells you that if the mass is larger, the speed is smaller. Inversely proportional to root M. For a mixture of gas in a container at thermal equilibrium, that means at constant temperature, the heavier mass has a smaller root mean square speed. Right? All that has the same temperature. Smaller mass, root mean square speed is going to be smaller. That's all. Okay. Sorry. If the mass is heavier, then it has a root mean square speed of smaller. If it's lighter, larger root mean square speed. Sorry, correction. Okay with that? Just play with the formula. That's all.
Oh, nothing so hard about that. Okay. The only latihan only lah.
Okay, we won't bother about that already.
What? Maxwell-Boltzmann.
Maxwell-Boltzmann distribution. Now you can find experimentally how the speed distribution at a particular temperature in a room or in a furnace is like. And you can draw the graph. Right? This axis is the number of particles. This axis is the speed. It's called the Maxwell-Boltzmann distribution. Give us the speed of air molecule distributed at a particular temperature. Molecules move with different speed, none with zero speed. Right? That's why there's none zero here. It definitely will have a speed one because there's always a collision. It will never be stationary. Some with very high speed. That's what it means. Some with very high speed, but most of it will be here. Right? From a range of speed, very low to very high. The molecules in gas are in random motion. In collision, some molecules gain kinetic energy, while others lose kinetic energy due to collision. So it's just like particles, they are always moving at random. They are colliding with each other. So collide, one will lose kinetic energy, the other one will gain kinetic energy. So the other will move faster, the other one will go slower. So that's why they all have different speed because they keep on colliding with each other. So area under the graph gives the total number of particles. Okay, so there's three terms you need to know.
Back again, sorry. So that means you will go up and then you go down lah.
Just memorize the graph, that's all.
Oh, okay. Okay. Maxwell-Boltzmann. Okay.
Right, and then there's three terms you need to know: probable, mean, and root mean square speed. Right, CP. I can call it VP or I can call it CP. is the most probable speed, is the speed of the most number of particles. Right? This is called the most probable because it's the speed of the most number of particles. A lot of particles with this value, Cp or Vp. Mean speed is the blue line. That's the mean speed. Root mean square speed. Okay? We see that root mean square speed is always the largest one. Root mean square speed is greater than the mean speed. I'll summarize it in formula form. Speed varies from 0 to a maximum. So that is not 0 lah. Okay. I'm very careless. Okay? Not 0 speed. From low to maximum speed. It will always have a value. Cannot be 0. It will always be moving. Unless it is a freezing point lah. Okay, so understand, most probable speed is the lowest, root mean square speed is the highest. Okay, how does the speed varies with temperature? You should be able to interpret. Okay, go back to the formula. As temperature of gas increases, the curve becomes flatter or the peak shifts to the right. That's the graph. Number of molecules with higher speed increases. Should be able to read the graph. Higher speed is here. Number of molecules here. Number of molecules higher speed start to increase. The graph shifts to the right. The height of the graph, that's the height. The maximum one, most probable speed become lower. Height of the graph has to decrease in order to maintain the same total area. Right? The area under the green graph and the area under the red graph must be the same. If it's spread out, then the height must go down. Or we can use this one to help us understand. Root mean square speed for higher temperature will be larger. That's why it has to shift to, the peak has to shift to lower, higher temperature, higher speed, sorry. So the mean square speed is going to be here. Previously it was somewhere around here. Okay, from our derived equation. So our equation is okay. It helps us understand why we get this type of graph. The most probable speed shift to the higher value. Right? Most probable speed shift to higher value, which is here. The peak is lower, right? That's the peak, or the height is lower. Root mean square speed increases with temperature. That's why I point out to you just now. Right? Don't worry about this one. This is just for info. These are the apparatus that we can use to determine the speed, the number of particles at a particular speed. That's how we can draw the graph. So any question to cover? Now we are going to degree of freedom and law of equal partition, 9.5.
Go to the previous slide, just no, previous
Don't worry.
slide.
As I said, just put in to show you that.
Oh, this one is trying to show the CP average mean, the one on the graphs lah, right?
Just know how to read the graph, know how to draw the graph, that's all.
And to determine which one is which.
Higher temperature,
which one they ask lah.
the peak becomes lower, and then those with higher speed will go further. So the curve is moving towards that side, that's all. That one shift down, the red one shift to the other side there. Higher speed, move to higher speed. Then you can understand.
No, but the root mean square speed for the green one is higher than compared to the red one, right?
Root mean square speed is higher, yeah.
Probable speed is higher for the red one.
Probable speed is still higher than the red one.
For the red one.
Because temperature will increase.
But for the root mean square speed is higher lah. For the green
increase
one.
all the speed, that's all.
Previous slide, please.
You just press the graph down, that's all. You just press this graph down, that's all. Then this graph will go to the other side, that's all.
Oh, you mean press the graph immediately? What?
Just like this is a plastic bag, that's all. You just press it down. So you press it down, you want to maintain the same area, the curve will move to the other side to higher speed.
Oh, same like the other slide lah just now. It's the same thing, right?
Then like your Toshe, you roll it up to something high, then you press it down, the area doesn't change, so you have to spread out. That's all.
Okay.
Or you can think of a cone. If you press the cone down, the cone have to go to a bigger area and then smaller height. Okay, let's go to the next one. Okay, so we have covered all this part. Now we are going to the last part, 9.5, degree of freedom and law of equal partition of energy. And the last part is the internal energy of the ideal gas. Okay, calculate the root mean square speed of gas molecule. Make sure you go and calculate that. Sorry, we have done that already. Make sure you go and try the past year paper or try the question from your book. Degree of freedom and law of equal partition. Define the degree of freedom of a gas molecule. Identify the number of degree of freedom of monoatomic, diatomic, polyatomic molecule at room temperature. Right? Key is room temperature. Explain the variation in the number of degree of freedom of diatomic molecule ranging from low to high temperature. State and apply the law of equal partition of energy. Okay, page 226. Okay, these are your three axes. I think the author draw it wrongly. The Y should go in. Okay, because we use our right hand, not our left hand. Okay, doesn't matter. There's the x-axis, there's your y-axis, there's your z-axis. What's degree of freedom? Memorize. Is an independent mode of motion or independent mode of acquiring kinetic energy. Dependent mode of motion or independent mode of acquiring kinetic energy. So number of degree of freedom of molecule depend on whether the molecule is monoatomic, one atom, diatomic, two atom, polyatomic, more than two atoms. Monoatomic gas, example, helium, neon, argon, have 3 degrees of freedom, which consists of X, Y, and Z direction, or Z axis. Right? They can move in any of these 3 axes, so you got 3 degrees of freedom. Diatomic molecule, example, hydrogen, oxygen, nitrogen. Besides translation means linear motion, molecules can also rotate about ZZ and YY, this one, turn around here. But X no point because very small. The normal inertia is very small, so we won't bother about XX. Right? Because the molecules are very small, inertia is very small, so we won't bother. So we consider 2 rotational only. X-axis and Y-axis. Rotation kinetic energy. X-axis is negligible because the moment of inertia of gas molecule about the axis is negligible, too small to consider.
So go to the previous slide, please. But teacher continue. Another one. Yes. Okay, just 1 minute. So monoatomic means 1, diatomic means 2, polyatomic means 3 or more, right?
Yeah, 3 or more.
So monoatomic means got linear motion X, Y, and Z. Okay, and so next slide, sir.
Diatomic can
This is
also go X,
diatomic.
Y, Z. Except
Okay.
rotation about the X rotation about X is negligible. So we won't bother about that.
Wait, I don't understand about the rotational thing. What's that?
Rotation motion about X, yeah?
You can only rotate around X lah.
Around X, that's all. This one
You
can
can't
go that
rotate
way.
anywhere else.
Can go clockwise, can go anti-clockwise. This one can go vertically. So it's far away from the center. And this one is very small moment of inertia. So
that means
yeah.
it's only XX, YY, ZZ only you can rotate lah.
Only ZZ and YY. XX no. Too small. Moment of inertia too small.
Oh, okay. No, but here that means the gas, when it comes to rotation, it only can rotate in its own axis only lah. So like example, Y means only Y. Is it?
As long as the moment of inertia is large, then we can consider the kinetic energy.
Okay, next one. Yes.
Right? Polyatomic also can have gas molecules with 3 or more atoms are called polyatomic. Water, carbon dioxide, ammonia. Right? Polyatomic molecule have 6 or more degree of freedom. 3 degree corresponding to translational, 3 to rotational. Right? OX, that is your O here. That's your O here. So at higher temperature, vibrational motion increase the number of degree of freedom. That is important. No? At high temperature, vibration will come in. At low temperature, we don't have to worry about the vibration kinetic energy. Okay.
Six degree of freedom. So that means for OX means you'll have 3 degree of freedom. OY means no. Each 2 lah, right?
Same like your translational, that's all.
Or rotational?
Rotation also the same. It can go into 3 different directions as long as the moment inertia is large.
Moment of inertia is the clue lah. But diatomic XX cannot, the others can.
Diatomic only x-axis, that's all. That means along its own axis, negligible.
Which means the key here is the moment of inertia has to be higher lah, or else it's negligible.
Yeah, most of them are higher for polyatomic, so you can consider as 3 rotational.
Okay.
Okay, you can summarize in your diagram there. Number of degree of freedom for various types of molecules discussed apply for gases around room temperature. Right? These are all for room temperature. The lower temperatures such as 50 Kelvin, rotation kinetic energy and vibration kinetic energy are negligible. Right? Low temperature, it doesn't come in for the atomic and polyatomic molecule. Hence, they have only 3 degrees of translational freedom. Right? Is below 0 degrees Celsius. 50 Kelvin is below that. So they only have translational for all the type of molecule, whether it's monoatomic, diatomic, or polyatomic. For high temperature above 750 Kelvin, that's very high. The number of degree of freedom increases. Diatomic has 7. Instead of 5, have 7. Vibration coming. 2 more than the room temperature. At this temperature, the vibration kinetic energy is now significant. Okay with that? Anything not clear? Okay. Total kinetic energy of monoatomic molecule, which we have derived. I can divide it into 3 different parts. And these are ideas that we use to understand our evidence. Right? Instead of this one, we break it into half kT. And then we can consider this in the x-axis, this the y-axis, this is translational kinetic energy in the z-axis. So we come with another law of equal partition of energy. States that the mean kinetic energy associated with each degree of freedom is half kT. K is Boltzmann constant. This is actually thermodynamic temperature. So for a molecule which has F degree of freedom, it just times F as well. Half kT times F. Right? That's for one molecule or one particle. For n particle, we just times n. Right? And then K we can replace with R over NA. Then this is just your n. These are two alternative formula that we can need to remember, or just memorize one of them and then derive the other one. That's all. Okay, so far?
Okay.
Anything not clear?
Go previous slides first. I just want to confirm only.
This is just to show you how we get the law, that's all.
That means 3/2 because of x, y, z lah.
3/2 because each degree of freedom got half kT. That's why we got 3/2.
And you have 3 axes, that's why you times 3 lah. Previous slide, another one. Okay, for temperature higher. Diatomic got 7. Okay. 2 more than that. But diatomic they put 5 there.
5, no? Diatomic we haven't calculated for you. We have gone over with you for diatomic is 5. Only polyatomic is 6.
6 plus, yeah, 6.
That is only for your translational and vibrational. Sorry.
Oh, the 5 is only
and
translational,
rotational.
is it?
5 is rotational only. Higher temperature, then vibrational will come in.
Oh, this is excluding what do you call that? Vibrational lah. It's only rotation lah. This 3,
higher
5,
temperature,
6.
then it got 7. Right? Where vibrational come in.
For polyatomic,
polyatomic also the same. The vibration will come in. So the number of degree of freedom will increase.
More than 7, is it?
Most likely. I don't think you need to go further than that. Just say it's increased good enough already.
Okay, one more previous slide. Oh, rotational and vibrational are negligible for the first one. Only translational are included, right?
With low temperature, right, 50 Kelvin or lower, then only translation kinetic energy for all of them. Doesn't matter whether it's monoatomic, diatomic, or polyatomic.
Oh, okay. Oh, no. Oh, yeah. They said for diatomic, polyatomic, they are negligible if it's lower temperature. But for one, there's no vibrational and rotational. That's why it's only translational, right?
The atomic got only two translational, two rotational, that's all. Only a higher
Monoatomic.
temperature about 750 Kelvin, then the vibration will come in. The lower temperature, you don't have to worry about vibrational kinetic energy.
Yeah, okay.
Okay, so we have completed our last section now. Right now, what is degree of freedom? Know this formula. All this formula you need to know. As I say, there's no shortcut. You have to do the past year paper to force this formula in so that you know which formula to use. So our last part is internal energy of ideal gas. Distinguish between ideal gas and real gas. Explain the concept of internal energy of an ideal gas. Derive and use the relationship between internal energy and number of degree of freedom. Right? When we say the internal energy of a system, the system can be solid, can be liquid, or it can be gas. Right? So we define it as the sum of the kinetic energy and potential energy. Right? Remember, with the molecules, we are interested in the molecules or the particles. So the particles have kinetic energy, and there's intermolecular force. So there must be stretching energy, we call potential energy. So we define it as sum of kinetic energy and potential of random motion of the molecules in the system. So that is mathematical way of representing. Kinetic energy is due to motion of the molecules, and potential energy is due to the forces between the molecule. Right? Intermolecular forces. In real gases, there are forces between molecules, especially when pressure of the gas is high. Right? When you press the gas at high pressure, the molecules are closer together. Same when it's at low temperature, right? They are near their boiling point. Then they are very close together. So the attractive force will be there. Hence, the internal energy of the real gases consists of kinetic and potential. So as long as it is far apart, it's ideal gas. But when you try to cool it or use high pressure, where it's going to solidify or become liquid, then we can expect the gas will behave as ideal gas, normal ideal gas, but as real gas. In ideal gas, there's no forces, there's no intermolecular forces between the gas molecule. Hence, the gas molecules have no potential energy. Right?
Only
Potential
kinetics.
energy come in because there is intermolecular forces of stretching and then release, stretching and release. That's all. Right?
So
Think of it
which
like
means
spring.
ideal there's no intermolecular lah. That means there's no
No
attractive force, only
intermolecular
real got
force,
lah.
so no potential.
If there was a intermolecular force, means got potential and kinetic also lah.
Yeah, if there's intermolecular force, then there's going to be stretching. There's going to be store energy. So that is potential energy.
Oh, okay.
Think of it as spring if you like. Intermolecular force is like a spring between the two atoms.
Okay.
Right? So you need to remember that degree of freedom and know how to calculate that. Okay, so we have derived for you this formula, degree of freedom. Either formula, F is the degree of freedom, U is the total kinetic energy of ideal gas, or N is the number of molecules. So we can read from this equation as an increase in temperature of the gas means an increase in kinetic energy. Right? Increase in kinetic energy means increase in internal energy. Right? For ideal gas. Internal energy of ideal gas is ideal monoatomic gas is directly proportional to absolute temperature. Right? From the formula. This is true regardless of molecular structure of gas. It doesn't matter whether it's monoatomic, whether it's atomic or polyatomic. right? Internal energy is proportional to absolute temperature as long as ideal. However, the expression U will be a bit different for gases that are not monoatomic. That means you have to add the term F in for this formula, that's all. Absolute temperature of gas is directly proportional to average kinetic energy. That means we can use absolute temperature as a measure of the kinetic energy per molecule, right? Or the kinetic energy of a molecule. Okay, so far?
Previous slide, Chair. Chair, you don't have to press that, Chair. You can just press the left thing only. The previous ones, Chair. The previous one, some more. Wait, Chair. Yeah, okay. Okay, 1 minute, Chair.
This is our definition.
So it's basically sum of kinetic and potential, lah, Chair.
Yes, of all the molecules.
All. Okay, it's
All
due to the motion.
Each molecule got different kinetic energy and different potential energy, that's all.
So potential is because of the force, kinetic is because of the
Intermolecular
movement,
force.
because intermolecular force, because kinetic means is moving what, so that's why it's only movement.
Yes,
Potential
kinetic
means
because
is
of movement.
force. Okay, next one, Chair. Next slide. No. Okay. In real gases, there are forces between, especially.
The only difference between ideal and real gas is there is attractive and repulsive force as well.
There is
Right,
intermolecular
force.
lah. Ideal don't have. Okay. Next
As
one,
long as
Chair.
you keep the temperature at the right temperature, then it becomes ideal gas.
Okay. Next slide, Chair. Oh, this is the fixed one lah. All translational got 3. Monatomic don't have. Only diatomic and polyatomic got. Only vibrational diatomic got 2. Polyatomic also got 2, I guess. An increase in temperature of the gas means an increase in total kinetic energy.
Yeah, can either memorize it or calculate out. That's all.
Wait. An increase in temperature of the gas means the increase. Oh, increase in internal energy means is when temperature increase, kinetic energy also increase at the same time.
Okay. For polyatomic, you
Okay.
just double this one, that's all.
Okay, next one, Chair.
It's all in your book. Remember, this is for atomic, monoatomic, that's all.
Monatomic means is only U, but the diatomic, polyatomic is different case lah.
You just have to multiply by F, that's all, number of degree of freedom.
Okay, next one, just like.
Right, and then need to know how to understand the formula. Right, if the temperature is double in Kelvin,
Yes.
then it's twice as hot.
Internal also
use
increase
Celsius scale cannot. Right, cannot say today is 20 degrees, tomorrow is 40 degrees, it's twice as hot. You cannot say that. But if it's
have to use Kelvin.
Kelvin, then you can say that.
Okay.
Okay with that?
Okay.
Temperature and kinetic energy, molecules in gas move about randomly at high speed. They collide with one another and with the wall container. Just summarize what we have learned. Collision with the wall give rise to pressure on the gas container. Right? And then when we measure temperature of the liquid, when we heat it up, right? When the thermometer is placed in a container of liquid, the molecule collide with the imparting the kinetic energy to the thermometer. The molecules of the hot liquid collide with the bulb. So kinetic is transferred to the bulb. So kinetic transfer and temperature increases. So that's why the temperature shown on the thermometer also rises. Right? Just to relate our experiment, that's all. At higher temperature, the molecule move faster or with greater kinetic energy. They give more kinetic energy to the bulb and the mercury rises higher. Hence, the reading of the thermometer is an indication of the kinetic energy of the gas molecules. We're just using this formula, that's all. And then we are just using this formula to relate mass, kinetic energy, and temperature. And remember, this formula is for monoatomic. If it's polyatomic, you have to modify accordingly. Kinetic energy is directly proportional to absolute temperature, we have said earlier. As the temperature is double, the kinetic energy per molecule increases. Air is a mixture of several gases, for example, nitrogen, oxygen, and carbon dioxide. In a sample of air, the mean kinetic energy of the nitrogen molecule is the same as that for oxygen and carbon dioxide. That means in a room there, the temperature is constant. So the mean kinetic energy of nitrogen, oxygen, and carbon dioxide are all the same. Carbon dioxide has a greater mass than oxygen. Hence, the kinetic energy is the same, right? Because the same temperature. Oxygen molecule, smaller mass, will move faster. Right? This is constant. Smaller mass, this one will be larger. That means it move faster. Right? Know how to read the formula, that's all. This is constant. Larger mass, smaller speed. Okay. When we say less speed, say again.
Acha, can you go like 2, 3, 4 previous slides? Acha? I just want to read back. Sorry. Just want to make sure that I understand. Some more. Wait, yeah, the 18. Okay. Okay, so next slide. Molecules in gases move that randomly. Oh yeah, this one they collide with one another. This one real gas, right? They collide with one another.
Doesn't matter. Real gas or ideal gas also behave the same in this condition.
This is ideal, is it?
You can think of ideal since we are dealing with ideal.
Okay. Collision give rise to the pressure of the gas. Okay. How you the 1/2 mv square equals to 3/2 kT.
This one we have derived earlier.
V square is 3 kT over m, isn't it?
We put C instead of, we use a different symbol, that's all. Instead of V, we use C, that's all.
Yeah, you substitute the C lah. Okay, next slide. When a thermometer, the molecules collide with it and imparting their kinetic energy to the thermometer. That means the thermometer increases lah.
When the molecules collide, it gives kinetic energy to the thermometer, the bulb of the thermometer.
Oh, this one is without increasing heat, is it?
Just to relate to you reality, why is the mercury rising in the bulb, in the thermometer, that's all? Because you receive kinetic energy, temperature rises, that's all.
I will receive kinetic energy from the molecules lah,
from the liquid molecule.
Surrounding it, yeah.
When the kinetic energy of the water molecule is increasing, then the kinetic energy of the thermometer will
increase.
Will rise as well.
Oh, okay. Next one, check. They give more kinetic energy. Okay, this makes sense. Hence the reading. Okay, next one, sir.
It's just to make sure you know how to use the formula, how to understand the formula. That's all.
KE is directly proportionate. Okay, as temperature increase. If temperature is double, the average KE per molecule increases as a mixture of several gases. In a sample of air, the mean KE of nitrogen molecules is the same that of oxygen and carbon dioxide molecules. Oh yeah. Wait, kinetic energy is same and for carbon and oxygen.
Yeah. Temperature, the same temperature, same kinetic energy. That's all.
Or not different because the one is diatomic, the
It's
other one
just the
is
speed and the mass
polyatomic.
different. That's all. But the temperature is the same, then the kinetic energy is the same.
Oh, okay, okay, yeah, sure. Okay,
Only the
next slide.
mass of the particle determine the speed of the particle. That's all.
Okay. Carbon dioxide have greater mass than oxygen molecule. Yes, that is correct. Since the kinetic energy is the same, oxygen molecule. Oh yeah, because oxygen has less molecules compared to carbon dioxide. Carbon dioxide is more heavy, oxygen is more lighter. That's why they move faster. Okay,
Yeah,
next slide.
this is constant. Temperature is constant. So
Yeah,
greater
temperature
mass, this
constant,
is smaller.
kinetic
That's
also
all.
constant. Mass is different, kinetic and temperature is constant lah. It's the same. So okay, yes, next one, sir. Next slide. Yes. This one teacher I haven't discussed yet, right? It is the
This
square
one,
root.
look at root
Yes.
means square speed. That's all.
Yeah. Okay, can wait, for mixture of gas in a container at thermal equilibrium, the heavier gas has a smaller root mean square speed. Oh yeah, lah, because the inversely proportional to mass, what? That's why. That means the higher the mass, the inversely proportional means then the gas will be smaller lah. Smaller
The
root
speed,
means square speed.
root means square speed will be smaller if the mass is larger. That's all.
Yeah.
Okay.
Mass is larger, heavier gas, then you'll have smaller root lah. Yeah. Okay.
Okay. So all these things you need to remember. Okay, just summarize for you, know how to derive that and know how to get all this equation. I think we have more or less completed everything. No time to do chapter 10 already. Unless you got time next week, you want to do, you can choose a day. If not, we have a class on Friday.
Okay, 9.6 teacher went through also.
9.6 done already. Summarize
Okay,
for you
okay.
here.
So yeah, I guess that's it lah, sir.
That's all for today.
I understand better now, sir. Thank you.
Understand that you need to do past year paper
Yes, correct. Yeah.
or try the questions to force it in. If not, you will forget everything. Since you are so
Yes,
confident that this
teacher.
topic is going to come out, then you better do past year question.
Yes, teacher.
Okay, we'll stop here.
Okay, thank you so much, sir.
Okay.
Bye-bye. Thank you.
Bye-bye.
Bye-bye.
Have a good day.
Have a good day to you. Thank you, sir. Bye-bye.
Okay.